MS Ramaiah University of Applied Sciences.
Hello students, let us discuss the experiment, design and test Darlington Amplifier. Aim of the experiment is to design, build and test a Darlington emitter follower amplifier with and without bootstrapping. An ideal amplifier should provide infinite input impedance and zero output impedance. However, compared to a BJT amplifier in common emitter configuration, the BJT amplifier in common collector configuration provides high input and low output impedance. Further, the input impedance of a FET is much higher than that of a BJT. To further improve the impedance characteristics, a Darlington amplifier in emitter follower CC configuration is used. The drawback of Darlington amplifier in emitter follower configuration is that the bias resistors tend to decrease the input impedance. Hence, a bootstrapping is introduced in the Darlington amplifier, which can further improve the input impedance of the amplifier. Such high input impedance amplifiers are frequently used as a buffer stages to isolate different stages of a cascade connection. In this experiment, a Darlington amplifier in emitter follower configuration is designed and the input and output impedances are measured. Further, introducing a bootstrapping mechanism, the Darlington amplifier's input and output impedances are again measured. The advantage of bootstrapping over a Darlington amplifier will be clearly understood by this experiment. The apparatus required to conduct the experiment are DC regulated power supply, breadboard and designed resistors, capacitors, function generator, CRO, decade resistance box and connecting probes. The circuit diagram for Darlington amplifier without bootstrapping configuration is as shown. The circuit diagram for Darlington amplifier with bootstrapping configuration is as shown. The block diagram for measurement of input impedance of Darlington amplifier with and without bootstrapping configurations are as shown. Procedure for design of amplifier. Choose a DC supply of 10 volt. Choose the Q point as VCE is equal to 5 volt and IC2 is equal to 4 milliamps. To obtain RE, VRE is equal to 5 volt, which is equal to IERE. Therefore, RE is equal to 1.2 kilo ohm. To obtain R1 and R2, IB1 is equal to IC2 by beta square, which is equal to 4 milliamps divided by 50 square, equal to 1.6 microamp. VB is equal to 0.7 plus 0.7 plus 5, which is equal to 6.4 volt. R1 is equal to VCC minus VB divided by 10 IB1, which is nearly equal to 220 kilo ohm. R2 is equal to VB by 9 into IB1, which is nearly equal to 470 kilo ohm. Note that in the calculation of R1 and R2, current in R1 is chosen as 10 times IB1. Let RL is equal to 10 kilo ohm. For smallest frequency of operation also, the coupling capacitor impedance is small. Accordingly, let them be 0.47 microfarad. Experimental procedure to obtain frequency response. Amplifier response. Connect the circuit as shown in figure. Adjust the input voltage between 0.5 volt to 1 volt at 1 kHz. Observe the output signal Vout and input signal Vin on a CRO. Repeat the above steps by connecting the circuit as shown in figure. Calculation of input impedance. Connect Darlington Amplifier circuit as shown in the figure. Measure output voltage VO with all the knobs of decade resistance box in 0 position. Increase the decade resistance box resistance till the output voltage falls to half of VO. The corresponding decade resistance box value gives input impedance.
Hi students, the name of the experiment is Design and Test Darlington Transistor Circuit. In this experiment, we are going to design a Darlington transistor with and without bootstrapping configuration and test the input impedance of both the circuits as well as output impedance of both the circuits. In this experiment, the following apparatus is required. A function generator, this is switch on, switch off button. It can generate sine wave, square, ramp, pulse, arbitrary waveform and noise. Using these settings, you can control amplitude and frequency of the sine wave produced by the waveform generator. 2 channels are available. In this experiment, we will use 1 channel. DC power supply, this is switch on, switch off button. It has 2 supplies. In each supply, it has voltage setting and current setting. This is plus terminal, this is minus terminal. Voltage setting can be used for coarse or fine adjustment. In this experiment, we will use 1 voltage source. CRO, its digital version. In this oscilloscope, waveforms can be visualized. It has 2 channels. For each channel, we can control the y-axis, that is voltage scale. This is second channel's voltage scale, this is first channel's voltage scale. Time scale for both the channels can be adjusted using this knob. These 2 are for vertical positionings of the waveform. This is for horizontal positioning of the waveform. Decade resistance box, DRB, it is an adjustable resistance box. It has 2 terminals. Across these 2, whatever resistance is set in the box will appear across these 2 terminals. Now this knob is used to change resistance in multiples of ohm. This knob is used to change in multiples of 10 ohm. This is multiples of 100 ohm. This is multiple of 1 kilo ohm. This is multiple of 10 kilo ohm. This is for 100 kilo ohm multiples and this is for 1 mega ohm multiples. So all these things can be adjusted to set a desired resistance value from the decade resistance box. Breadboard, this line here is completely connected and it acts as 1 node. Like that, 2 such nodes are there on the top of the breadboard and bottom of the breadboard. This half and this half of the breadboard are separate. This 5 dots represent 1 connection. So 5 dots in any column represent 1 connection. Here also 5 dots in any column, they represent 1 connection. Resistors, these are the resistors used in this experiment. This is 220 kilo ohm resistor. This is 470 kilo ohm resistor. This is 1.2 kilo ohm resistor and this is 10K resistor. Capacitors, these are 0.47 microfarad capacitors, 2 in number. This is 10 microfarad capacitor, 1 in number. It has a polarity. The longer wire is plus and the shorter wire is minus. Longer wire is positive, shorter wire is negative. Transistors, we use 2 such transistors. A BJT comprises of emitter, base and collector. To see the emitter, first you have to see where this notch is there, this small notch here. That adjacent terminal to the notch, this is emitter, next base, next collector. These are the connecting wires to connect the circuit, and connecting probes used to connect function generator and oscilloscope to the circuit. Now let us start connecting the circuit based on the circuit diagram. First take a breadboard, then take an SL100 transistor. So connect emitter, then connect the base, then connect the collector. So emitter, base, collector. Take another SL100 transistor, connect base of this transistor to emitter of first transistor. So base of this transistor is connected to emitter of other transistor, previous transistor. Now connect collector of this transistor to already connected collector. So both the collectors are shorted. So both the collectors are shorted. Take emitter terminal and connect it to a nearby node. So emitter terminal, then base terminal connected to first transistor's emitter. Both the collectors are shorted here. This is base of first transistor. So this forms a Darlington configuration. Now take 220 kilo ohm resistor and connect from base of first transistor to positive supply. So base of first transistor to positive supply. This is 220 kilo ohm resistor. Now take 470 kilo ohm resistor and connect from base of first transistor again to ground. So this line we will use as ground. This line is positive supply. Now take 1.2 kilo ohm resistor and connect from second transistor's emitter to ground. Now take 0.47 microfarad capacitor and connect from base of first transistor to a nearby terminal. So capacitor, base of first transistor to nearby terminal. Here we will connect function generator and CRO's channel 1 later. Now take another coupling capacitor 0.47 microfarads, connect from emitter of second transistor to a nearby terminal. So this is the output. We will connect this to CRO channel 2 later. Now take a connecting wire, connect from positive of supply DC supply to positive supply line. So this is the positive supply used for the circuit. So positive of first supply is given to the positive supply. Now take another connecting wire and connect from negative of the supply to ground. So this is the ground wire used in this circuit. So negative of supply is connected to ground line. Now take one function generator probe and connect it to channel 1 of function generator. Here from the positive of the function generator, connect a connecting wire and give this to the coupling capacitor at the base. So first transistor's base had a coupling capacitor. To that capacitor, function generator positive is connected. Take another connecting wire and connect from negative of function generator to ground. So negative of function generator to ground. Now take CRO probes, connect one probe to channel 1 and connect the second probe to channel 2. So channel 1, the positive and negative are here. The channel 2, positive and negative are here. So take a connecting wire, connect from positive of first channel and give this to function generator's positive. So function generator's positive is connected to CRO's first channel. Function generator's positive is connected to CRO's first channel. Now take another connecting wire and connect from negative of CRO, first channel CRO, and put it in ground. So negative of first channel of CRO to ground. Now take second channel CRO probe and connect using another connecting wire. Connect from positive of second channel and give it to coupling capacitor 0.47 microfarad capacitor here. So from the capacitor to the CRO second channel. Now connect negative of this CRO second channel to ground. So two CRO channels, one is given at input, one is given at output, and grounds are common with the ground here. Now take another connecting wire and connect from both the collectors to power supply. So both the collectors are connected here. This is the joint. So both the collectors joint and give this to positive of the supply. So positive of the supply. So collectors, both the collectors are joined and that is joined to power supply. Now take a DRB. So this is decayed resistance box. Take the decayed resistance box. Now take connecting wire. Connect from positive and leave this wire to be connected to your circuit when necessary. Take another connecting wire, connect from negative of DRB so negative of DRB and leave this to be connected to your circuit. Because this is a resistance, polarity doesn't come into picture. So plus and minus have no significance because this is a resistance. We will connect this to verify the outputs later. Now this completes the connections of the circuit. Now let us test the circuit for its input and output impedances. So first switch on the DC power supply but make sure the voltage knobs are in the minimum and current knob is in the maximum. Then switch on the supply. Now adjust the voltage such that it is 10. So now 10 volts is being supplied to the circuit. Now switch on the function generator. Press sine wave. Adjust frequency as 1 kilohertz and amplitude as 1 volt peak to peak. So frequency is 1 kilohertz, amplitude is 1 volt peak to peak, and now this input provided to the circuit by switching on this button. So now signal input is sine wave signal input is provided to the circuit. Now switch on the CRO. Press auto set. Now this waveform is the input, this waveform is the output. You can see that input and output are perfect sinusoids. Now let us measure input impedance and output impedance. For that we will hide the input signal. So double press of this button will make that hide. Now adjust this waveform such that it appears in the middle. Peak to peak is 1 volt. Input what we gave is also 1 volt peak to peak. Now adjust the voltage scale such that it looks big. Now this is 5 boxes in CRO. 5 boxes in CRO is the output signal. Now we will insert the DRB to measure input impedance. So take the DRB, input where the function generator and CRO are connected, these two wires put it in a nearby node. So function generator and CRO are removed and kept in a nearby node. Now provide the DRB between these two, that is capacitor's edge and this function generator edge. Between the two you should have your DRB. Now take the DRB, make sure that all the knobs are in the minimum position, and this DRB should be inserted between function generator and input to the circuit. Hence remove the function generator wire and the CRO wire to separate position. So function generator and CRO input both are connected to a separate position, and now insert the DRB between the coupling capacitor and this junction. So between the coupling capacitor and this junction. So now because we have inserted the DRB and all the resistor knobs are in 0 position, it is as if we have not introduced any extra resistance. Hence the output should not change. So let's look at the CRO. So input and output waveforms, input is in first channel, output is in the second channel, and it is same as before we inserted this DRB. So before insertion and after insertion, the output waveform is the same. Now hide the input, adjust the output waveform to middle. Now this is the output waveform shown by the CRO. You can see that it occupies two boxes. Now in order to find the input resistance, we have to make sure while the DRB resistance is being changed, it becomes one box full instead of two boxes. So now we will start adjusting the DRB such that the output is occupying only one box. Now start changing the DRB in steps of 10K. So as you change this, the CRO output keeps changing. Now we have set 200 kilo ohm resistance, 200 kilo ohms. Now you can observe the CRO. If you adjust the waveform, it occupies one box instead of two boxes. So that means the input resistance of this circuit, the complete input resistance of this circuit is 200 kilo ohms. That is shown by the DRB. This completes Darlington transistor amplifier. Now we will include bootstrapping to this circuit and again check the input impedance. Whether it will be more than 200 kilo ohms or less than 200 kilo ohms, we will figure out. So for that, first switch off the power supply. Remove the DRB. And put the function generator and CRO position back at the coupling capacitor. So now the function generator and CRO input are placed back at the coupling capacitor. So now we will make this circuit with bootstrapping. This is Darlington amplifier circuit without bootstrapping. Now we will make it with bootstrapping. For that, at the base of the first transistor, we have inserted 220 kilo ohm and 470 kilo ohm resistors. Both those resistors have to be lifted and kept in a separate node. So we will do that. So 470 kilo ohm resistor I have removed and it is kept in a separate node. Again 220 kilo ohm resistor, it is removed and kept in the same node as that of 470. So this is 470. So 220 also should be joined here. So 220 kilo ohm resistor between supply and new node. 470 kilo ohm resistor also between ground and the new node. So these are the two resistor changes. Now take 10 kilo ohm resistor, take a 10 kilo ohm resistor and insert one leg in this new node. So in this new node we have one more resistance, that is 10K, and this other edge of the 10K, that is other leg of 10K, put it to the base. So put this other leg to the base of first transistor. So now 10 kilo ohm resistor is between this new node and base of the first transistor. Now take 10 microfarad capacitor and positive of this capacitor connect to this new node. So positive of this capacitor we will connect to the new node and negative of the capacitor give it in a nearby terminal. So negative of the capacitor in a nearby terminal. So positive connected to the new node, negative connected to a nearby terminal. Now take a connecting wire and connect this negative leg of the capacitor connect the negative leg of the capacitor to second transistor's emitter. So second transistor's emitter is here. So second transistor's emitter is connected to capacitor's negative leg. Now the circuit is again Darlington transistor with bootstrapping circuit. For this we will check the output first. So now switch on the power supply. Now check the CRO. We will press auto set. You can see that input yellow color signal and blue colored signal output both are the same as we have seen earlier. The only change is we have inserted two extra components and that is called as bootstrapping. Now we will check what will be our input resistance for this circuit. For that purpose, hide the input signal, lift the output signal so that it is in the middle. Now you can observe that it is again two boxes full. Now we will attach the DRB and then make it half. That value of input resistance we will write. So take the DRB. Again make sure that all the knobs are in the minimum position and insert this between function generator and coupling capacitor of the circuit. So first remove the function generator wire and keep it in a nearby node and also the input of the CRO in a separate wire, separate node. So between this and the input coupling capacitor we will attach our DRB. So DRB is one terminal here, second terminal here. So now DRB is connected. So now that we have inserted the DRB and all the knobs are in zero position, you can observe the output. It is again two boxes full of sinusoid. Now we will start changing the DRB resistance such that this occupies only one box instead of two. That resistance value will be the input resistance of the circuit. So now let's see the DRB. Now start changing the DRB. As we change the DRB resistance, the output waveform keeps changing. So now let us look at the CRO. Right now the impedance value kept here is 1 mega and 100 kilo ohms, that is 1.1 mega ohms. Now let's check what is there in the CRO. So you can observe that the CRO is one box instead of two boxes peak to peak at a value of 1.1 mega ohms in the DRB. Hence input impedance of this circuit is 1.1 mega ohms. If you compare this answer with earlier answer, that is without bootstrapping, the input impedance of without bootstrapping is 200 kilo, but this is 1.1 mega. Hence there is a drastic increase in the input resistance. Thus the purpose of bootstrapping is solved. This completes the experiment.
At MSR UAS, we spark your imagination unlike any other.